Hi, everybody. This is Bruce for GOTO, and I'm with Groxio Learning, but I have a special guest for you today. I've got Sean Moriarty, and he's the creator of the Axon project and the co-creator of the NX project as well. This is all things machine learning in Elixir. You want to tell the audience about yourself, Sean?
Sure. So my name is Sean Moriarty, originally from Philadelphia, Pennsylvania. I am the author of Genetic Algorithms in Elixir, and I also have a new publication out called Machine Learning in Elixir. Worked in the machine learning ecosystem in Elixir for quite some time now, and I'm excited to talk a little bit about my new project.
Yeah, and this is an interesting story because as many of you might know, Elixir has not always been known as a great language for machine learning. And so I think that you might have knocked Jose, the creator of Elixir, out of his chair when you wrote the first book about genetic algorithms and machine learning. Could you tell us a little bit about that?
Yeah, so I was really interested in genetic algorithms and evolutionary algorithms in college, mainly for applications in like sports betting in particular, because sports betting is very similar to like financial theory, investing basically, so portfolio theory. And there's a lot of tie-ins with using genetic algorithms and evolutionary algorithms for optimizing a portfolio for risk and reward. And so I was really interested in genetic algorithms, evolutionary algorithms, and I was also really interested in Elixir, but Elixir is not a good language for doing any of this stuff. The Beam, the virtual machine that Elixir runs on, the Erlang virtual machine, is not good for numerical computations. It's well suited for like concurrency, building fault tolerant applications, but numerical applications were not something that it was very good for. But I decided I was just going to write genetic algorithms in Elixir anyway. And so I had created a project for creating genetic algorithms, solving some toy problems basically with genetic algorithms. And I thought it was something that other people might also be interested in. So I kind of threw a Hail Mary over to the Pragmatic Programmer, the Pragmatic Bookshelf, who's the publisher behind the Pragmatic Programmer, about a book pitch basically for genetic algorithms in Elixir. And miraculously, they ended up accepting it. The book came out in, I think, February of 2020, or maybe it might have been October of 2020. And after that, I got in touch with Jose Valim, who's the creator of Elixir. And he basically was like, hey, so I thought this was pretty interesting. Do you want to start working on machine learning projects in Elixir? And I thought that would be pretty awesome. So we kicked off that project around the same time, October 2020. And 3 years on now, we've got everything from deep learning to traditional machine learning. You can use pre-trained transformers, a lot of pre-trained models just directly from Elixir itself. And our performance is pretty competitive with the Python ecosystem. And we have some pretty good abstractions for deploying machine learning models as well.
I want to slow you down a little bit because we've glossed over some pretty interesting things there. So I've got to tell you, I've got to make an admission for the first time on this podcast. I saw that initial book proposal come through, and I said, this is the wrong thing for Elixir. I'm the editor or kind of the line editor of the Elixir line of books at the time. And I said, this is really interesting stuff, but this is more interesting from an academic perspective. So I said, I don't want to kill this, but I also don't want to kind of give people false hope, right? So what I did is I said, okay, this is interesting academically. So does anybody else want to take a shot at this? And another editor stepped up, and the rest is history. But one thing is interesting is that there's a pretty blinding moment in time that just went very quickly where Elixir was not a good language for these kinds of applications to the time that Elixir became that. And that's what NX is about. Could you tell us a little bit about what NX does before we get into Axon and the machine learning stack?
Yeah, so NX stands for Numerical Elixir, which is essentially the foundation for the Elixir machine learning ecosystem. The NX project started out, so early on, we were trying to make a decision on how we were going to design the libraries. And Elixir and Erlang, they have this concept of native implemented functions. They're essentially just a way you can write C bindings to some native library and then get it to work with the Erlang virtual machine. And one of the paths we could have taken was saying, okay, well, these libraries like TensorFlow and PyTorch, they offer C and C++ libraries. We can just essentially build directly on top of that. And it would have been a pretty quick win. We could have gotten something up and running very quickly. The problem with marrying yourself to another ecosystem is you are essentially blocked anytime they have an issue. And, as a smaller consumer of their native libraries, you might not necessarily have the biggest influence over the bugs they're going to fix and the things they're going to prioritize. So we made a very intentional decision to not build the library dependent on other ecosystems upstream like that. So NX, for those that are familiar with the Python ecosystem, is very, very similar to NumPy, but NX has the additional abstraction of like pluggable compilers and backends, which means that NX itself just implements a behavior, which is, I guess, similar to like an abstract class for those coming from object-oriented programming. Essentially, it's just a contract for people to implement their own implementations of some of the numerical routines that we have in NX. So, for example, NX has something like nx.cosine or nx.cos in this case, and library backend and compiler implementers can implement their own versions of cosine for targeted hardware or specialized routines that are accelerated in some way. And the first compiler we implemented was XLA, which is Google's accelerated linear algebra. It's basically a machine learning compiler for taking these numerical programs and compiling them to the CPU, the GPU, and Google's TPUs, these accelerators. So NX really serves as the foundation for our entire ecosystem. It also implements automatic differentiation, which is important for implementing some of the optimization routines used in Axon, which is a deep learning library. But it sounds like we're going to get to that a little later. So that's pretty much it about NX.
I love the idea that since you're snapping out this whole numerical model and then kind of the whole way that you think about storing tensors, right? Mm-hmm. That these are concepts that are just kind of ripped out of the language and snapped in. And to make that serviceable, you did something fairly brilliant in there. And that's taking a traditional function definition and then offering an alternative implementation. Can you tell us just a little bit about defin?
Yeah. So NX introduces this idea of numerical definition. So in Elixir, functions are declared with the def keyword. In NX, you get something called defn. So it's just literally like def and then an n at the end. And that's a numerical definition. And these numerical definitions support a tiny subset of the Elixir programming language. So it's a little more strict. One of the things that we noticed, we tried to model a lot of the library off of JAX, which, it's a library. It offers basically the NumPy API, jax.numpy. But it supports just-in-time compilation. As a part of that just-in-time compilation, you get some interesting behavior. So JAX functions, JAX JITted functions, they have to be completely pure. So any side effects that happen, they only really happen once in these programs, and they have to have some interesting like static shape and type constraints. And it was difficult for people transitioning to write JAX to get around like, hey, Python has these really flexible abstractions. Like people like writing Python because it's flexible, and JAX-JIT was not flexible. So we made kind of an intentional decision to have a completely separate abstraction from traditional Elixir functions, because we wanted people to understand that when you write a numerical definition, it's going to get JIT compiled. Anything that's like side effecting is not gonna work very well with what you want to do. And so we wanted to keep that abstraction completely separate from the core language. So when you write a numerical definition, it essentially gets immediately compiled and targeted to whatever the compiler you choose is. So in this case, if you're using something like EXLA, which uses Google's XLA, your numerical definition will get just-in-time compiled to the CPU or the GPU, depending on the client that you choose, for the inputs that you give it. And it's a very interesting abstraction because it's something that just extends the language. Like it didn't require any changes to Elixir upstream. Elixir itself is just a really, really flexible language with metaprogramming and some of the other things you can do. So we didn't have to make any changes to Elixir upstream. It's just something that were able to natively support given what Elixir has.
Which is really beautiful, right? It's like you can snap these guardrails right onto the system and everything just works, right? So I hope that the listeners are starting to get a sense that rather than building something quick and dirty and making a library type decision, this is actually something a little bit more related to the infrastructure in building up layer by layer slowly. And then let's talk a little bit about the next layer, the Axon layer. So what is Axon?
Yeah, so after the NX project started to show some initial successes, we wanted to get like real applications of what we were building. And so the first, I would say, real concrete application was neural networks, because deep learning and neural networks today are almost synonymous with machine learning. People say machine learning, and like 90% of the time people are talking about deep learning just because of the popularity of large language models and some of these other pre-trained models for computer vision and natural language processing. So while there is like traditional machine learning, and we do support traditional machine learning, we really targeted neural networks because at the time they were very, very popular. And that was the first thing we wanted to prove. We were able to do that, because if we were able to do that, then we were essentially able to do anything we wanted to. So Axon is a library for creating and training neural networks in Elixir. It has a very similar API to Keras, TensorFlow Keras, as well as some other ideas stolen from the PyTorch ecosystem. So I am I would say, machine learning framework junkie, and I spend a lot of time just reading about different approaches to solving machine learning problems and different like library design decisions that the creators of PyTorch and Keras and some of the projects in those ecosystems have made, and looking at the complaints of people and trying out different things and seeing what works. And so Axon borrows a lot of ideas from these other ecosystems to make it easy to create composable neural networks and then also train these neural networks. And it's a fundamentally different approach than what you see in the Python ecosystem, just completely out of necessity. So obviously Python supports those object-oriented abstractions, and Axon, being built on top of a functional programming language, has to build on functional constructs. So it's a little difficult in terms of like comparing apples to apples, something that's implemented in Keras and something that's implemented in Axon. But it is very similar. It will feel very similar to someone coming from another ecosystem directly into the Elixir ecosystem.
Yeah, and this is cool, right? So one of the things that I've noticed is that by slowing down, we're kind of hitting this point where everything seems to be happening at once. It seems like having the Elixir infrastructure underneath, by slowing down and getting the abstractions right, all those things can be brought to bear to the overall project. So can you talk about the impact of Axon and Index on the Elixir ecosystem?
Yeah. So I want to hit on the point that like starting out slowly, how fundamentally important that was to what we wanted to do, because I think this is happening a lot in the Python ecosystem now. PyTorch 2.0 has made a huge like effort to rewrite a lot of their internals in Python, and there's a lot of reason for that decision. But one of them is obviously just like from a maintainability perspective. Python, for better or worse, is much more approachable than C++ as like a language for writing compilers. And writing for someone who's just coming into the PyTorch ecosystem, it's a lot easier for them to just look at some Python code that maybe implements like some of their backends for writing these numerical programs than trying to figure out like decipher C++. And so we had that kind of same inclination from the beginning that we should keep as much of what we were building in Elixir as possible, because it's more maintainable, it's more approachable, and it was going to just be easier for us to work with and to work fast and build on top of, because neither myself nor Jose nor any of the maintainers who have come on after the fact of the original project, like Paolo and Jonathan, none of us are C++ people. We all are Elixir programmers, and so keeping everything in Elixir allows us to work a lot faster than we traditionally would have, because we're a very small team of people writing this. It's basically 4 or 5 people that are really the core maintainers of the NX project. And we're able to implement features significantly faster just because we're working in Elixir, and only reach into C++ and C and Rust and whatever when it's absolutely necessary. Now, the overall impact that NX and Axon have had on the Elixir ecosystem, I would say it's been pretty large, especially in the amount of time that the projects have been out there. So we really are only around 3 years into these projects, and there are already some successful applications of these libraries being used in production. People, I think, are excited about the prospect of using machine learning in Elixir, especially for companies that are using Elixir for their actual deployment environment, their backend services and stuff. It's a lot, I would say, easier for someone like them to maybe get thrown a model from the Python ecosystem from their data science or machine learning team, and then to implement, essentially an inference pipeline directly in Elixir without having to call out to another service or build some on top of some complex microservices stack. So it has definitely had a pretty large impact, and I'm excited to see where the ecosystem grows.
Yeah, we're starting to see all these little pop-up projects, right? And that's always an indication that you're doing something well on the abstractions end, right? So we've talked a little bit about the impact of machine learning on Elixir and the idea that this is unexpected and pretty exciting, and has definitely hit this critical mass where everything is rolling now. But we haven't talked about the impact that we might see of introducing Elixir to machine learning. Can you talk about why that might be interesting to us?
Yeah. So anytime you try to, I guess, penetrate an additional market from a programming language perspective, you have to, I would say, do it carefully and think hard about why someone would choose to use your language for whatever it is that they're doing over what they're used to. And particularly in machine learning, Python is so entrenched, and it's for good reason. There's a lot of really great abstractions and great libraries in the Python ecosystem. It's friendly for, beginner programmers who might have an academic background and they're interested in some aspect of numerical computing or machine learning. It's very easy to write, pick up Python and just run with it. So when we first started these projects, I think a lot of people thought we were kind of crazy because, trying to target something that is so entrenched like Python is in the machine learning ecosystem, other languages have tried to do this, and it doesn't always have the best results. And so we were trying to, I guess, tread carefully from the very beginning that, we don't necessarily see these projects as overtaking Python as the primary language for machine learning. But we wanted to give people who were using Elixir and who were interested also in Elixir kind of an alternative to some of their original workflows. And as the projects have matured, we're kind of identifying areas where our projects could have a significant advantage over some of the same projects in the Python ecosystem. So I think one of those is in our serving abstraction, which is servings in the world of machine learning are just an inference. It's essentially just a fancy way to say that we're going to get inferences from the model in production. And in the Python ecosystem, there are 5 or 6 serving projects, and they're all separate services like Torch Serve, TensorFlow Serving, Kserve, which is a Kubernetes thing. There's all these abstractions for essentially overcoming, I think, some of the shortcomings that Python has as a language for deploying machine learning infrastructure. Whereas in the Elixir ecosystem, we don't necessarily have some of the same shortcomings. So we have this abstraction, which is NX serving. It is essentially a data structure or a behavior that wraps what you would see in a production inference pipeline. So it encapsulates pre-processing, actual inference of the model, and then post-processing. And the NX serving abstraction is very, very simple, but it supports some pretty insane things. Because of the way Elixir is built on top of the Erlang virtual machine, NX serving supports distribution just natively. So if you have a cluster, you can spin up, multiple servings, and they're load balanced automatically between the nodes in your cluster. Or if you have, let's say, multiple GPUs, you can partition inferences between multiple GPUs. And it's a very scalable application. It's a very scalable abstraction, and it's also you get all of the goodies that you would get from building on top of the Erlang virtual machine to begin with, fault tolerance and good concurrency, and the ability to build robust machine learning applications on a battle tested and production ready virtual machine.
So it sounds kind of like there are reasons to use Elixir, and there are reasons to do machine learning, and so the reasons to use Elixir don't go away just because you're entering this other space, right? So in some ways, all the things that Elixir does are becoming table stakes, right? And all the things that machine learning does are becoming table stakes. And so once we can bring those two things together, some pretty exciting things happen.
Exactly. Yeah. And we try as best as we possibly can to make the ecosystem, interop well with the Python ecosystem. So we have this library called Bumblebee, which supports a lot of pre-trained machine learning models in the Python ecosystem. So essentially what Bumblebee is it's very similar to the Hugging Face Transformers library, which has a ton of pre-trained transformer models and some other computer vision based models like ResNet and whatnot. And we built Bumblebee as kind of like an intermediary between ourselves and the Python ecosystem. So we're able to take pre-trained like PyTorch models, convert them to what you would need to use in Elixir, and then use them directly in your Elixir applications. And we also support a lot of the same tasks as you would see in the Python ecosystem. So Hugging Face has like pipelines is what they call them. We call them servings. These pipelines support anything from named entity recognition to text classification to image classification to text generation. We support all of those as well. So if you are working with a data science team that, they're not going to want to switch right away from using, Elixir, from using Python to Elixir. So they can still work in Python. They train their models in Python. And then as long as you have like trained or saved weights, you can kind of throw them over to your backend team, and they can write the inference pipeline in Elixir. So we're very intentionally, I think, friendly, or try to be friendly and supportive of the Python ecosystem because, in some ways it's a necessity. There's no reason to completely disregard all of the incredible work that's been done in the Python ecosystem because it's just unrealistic to think that we would be able to catch up with 30 plus years of a head start in the space, right? So we try to support interop. We also support Onyx, Open Neural Network Exchange, so you can transfer, or you can essentially take Onyx models that you've trained, in the Python ecosystem and run them with some of the NX abstractions. So we have what's called like a storage only backend, where you use the NX serving abstraction as a way to implement an inference pipeline, and it's backed by the Onyx runtime. So there's a lot of reasons to use Elixir without actually having to switch from using Python.
Yeah, can we talk about some of the use cases that you might have seen in Bumblebee? What can this thing do, and where? Well, first let's talk about what it can do.
Yeah, so Bumblebee can do a lot of the same things that the Hugging Face Transformers library can do. So we support a pretty large, I would say, relative to the size of the Transformers library. We have a pretty large coverage of the pre-trained models, at least the ones that are the most popular. So you could take something like a pre-trained BERT and do text classification with that. You can fine-tune the models and pre-trained models from Bumblebee for downstream applications. We also support, like I said, these servings. So one example that I've seen used is in entity recognition, taking essentially extracting like proper nouns out of some structured or unstructured data like text, and identifying like, hey, this is a person, this is a place, this is an organization. And then we also support like text generation. So we do support some of the latest and greatest chat models out there. So Llama, for example, is one of the ones that we do support. You can build on large language models in Elixir without having to actually, shell out to Python or something else. So there are a lot of very powerful applications. And one of the strengths of Bumblebee is that it's a very low code, I would say, library. So, getting up and running with a text generation pipeline is probably like 4 lines of code and you're ready to go. And that's pretty powerful, especially for us, because in the Elixir ecosystem, we don't have a ton of people with machine learning experience. So Bumblebee is able to give them access to like a quick win.
I've talked to a number of people who have started to make some Bumblebee contributions. They said it's really remarkably easy. So it seems like, once again, the abstractions are good.
Yep, and Bumblebee builds, it's an 100% Elixir library. So really the only libraries we have that touch any sort of native code are compilers for NX. NX itself is a 100% Elixir library, and then it's the compilers that NX touches that are written in C and C++ and Rust and some of the other native languages. But everything from NX to Axon to Bumblebee, it's 100% Elixir. So it's a very approachable library. The abstractions are very, I think, easy to understand once you kind of peel back the layers. So it's very powerful.
So we've spent a little bit of time embracing Python, and I'm not going to say take your shot now, but what are some of the things that Elixir does that may make it maybe even better for machine learning than some of the other machine learning languages?
Yeah, I think the obvious one here is concurrency. Python with the GIL is it's kind of difficult to achieve the same, I would say, level of concurrency that you can achieve in an Elixir application. Elixir is really, really good for building like robust, fault tolerant, highly concurrent applications. One of the things that originally drew me to trying to do machine learning in Elixir was there's a book from the Pragmatic Bookshelf as well, Concurrent Data Processing in Elixir. And it's about building these like robust data pipelines, highly concurrent data pipelines. And that's something that you see a lot in machine learning workloads, and achieving some of the same, I guess, throughput that you would get in the Python ecosystem, the Elixir ecosystem is just trivial. There's a lot of like abstractions in the Python ecosystem that are essentially just like wrappers around C and C++ implementations, whereas you don't have to do the same thing in the Elixir ecosystem. So, for example, like tf.data is a data input pipeline for TensorFlow, and the same exact things you can do in tf.data, you can just do natively with Elixir because it just supports this concurrent data processing out of the box. And then a lot of the OTP abstractions in Elixir are, I would say, very, very well suited for building these like robust machine learning applications. So I'm just now, because I was not getting into the language, I liked Elixir aesthetically, but I didn't necessarily appreciate the OTP abstractions as much. And now recently I'm starting to get really into the OTP abstractions and building more on what the language is designed to do, and seeing how it connects really well with some of the things you want to do in like the ML ops lifecycle, which is the lifecycle for deploying machine learning models, and trying to identify, I guess, use cases for this is like really powerful, and this is how this benefits the machine learning ecosystem. So there's a lot of things that I think Elixir does better than Python, just out of the circumstances of the language. The language is designed for telecom platforms, right, or built on top of a language designed for telecom platforms. And it turns out those abstractions are also really good for building like robust web applications. And so that's one thing, or those are some of the things I think that Elixir does just better than Python as a consequence of how it's built.
And what about immutability? Does that play a role, or does the lack of immutability play a role in the way that you've had to build Axon and layers versus the way you might have done it with something like Python?
Yeah, I think immutability is an interesting one because for like mathematicians and people who are coming from like an academic machine learning background, the immutability and like the functional style of writing things in Elixir kind of fits better with what you would be used to seeing like mathematically. Immutability, I think, helps a lot about reasoning about some of these more complex, highly concurrent data pipelines. But then from like just the I guess aesthetic perspective, writing a program, a numerical program functionally, I think makes a lot more sense than some of the things you would do in the Python ecosystem. So like, for example, like TensorFlow and PyTorch both support what are called in-place operations, where essentially you have a buffer that's you have a tensor that's backed by some buffer, and you can perform like an in-place sort where that data is completely changed, completely overwritten. And I've had experiences in the Python ecosystem where I do something in place, and then you get some pretty wonky results because you don't realize that you were mutating some data like 4 or 5 lines up, or somewhere at the beginning of the program. You don't necessarily have that same exact problem in the Elixir ecosystem because everything is immutable by default. So from a performance perspective, it's something that kind of hindered Elixir from the beginning, because with immutability, that obviously like kind of implies some additional copies. But with this compiler, this JIT compilation concept that we introduced with NX, we kind of completely bypass any of the issues we have with immutability, because NX works on like a multi-staged programming model. So when you write a numerical definition, it gets lowered to an NX expression, and then that gets compiled into a program. So it's not eager by default. It's a very, I would say static workflow. And so you don't necessarily have the same performance hits with immutability that you would if you were just, working natively in Elixir.
You just kind of carve down how much, what your primitive operations are, right? You expand those a little bit and contract them in other places, right? And that's pretty cool. Yeah. So I have a couple more questions for you. Do you have some favorite moments on of when where this whole roller coaster ride has taken you? Are there some favorite moments?
Yeah, there's definitely a lot of like stories related to these projects. Early on, I don't think there was a lot of, I would say, initial roadblocks to success, and like we have come a long way. But in the beginning, there was not like a guarantee that the projects were going to work out. It was kind of just more of an experiment. So I can distinctly remember some of the initial like trials and tribulations with these projects. One, for example, was the first time we got NX and to compile a program to the GPU. That was a little rough. So I go into a deep dive on Twitter about this, but the Erlang virtual machine does some interesting things, like intentionally. And when you're dealing with subprocesses, external programs, you can run into some problems. So I have a deep dive on Twitter about that. But I do distinctly remember it took like a few days to track down some issues we were having with, why could we not compile a program to the GPU? And then we had kind of a breakthrough moment. We're able to, and I think it was the program we were compiling was just like 1+1 or something simple. Like it was nothing crazy, but that was pretty awesome when that first happened. And then I remember we had some initial difficulties with AutoGrad. So Jose wrote a lot of the AutoGrad like infrastructure. I think he honestly has probably rewritten it like 6 or 7 times in the life of the project. And I remember how frustrating it was at times to get some of the things to work, because AutoGrad is not necessarily, or automatic differentiation is not necessarily something that's like straightforward to implement and straightforward to implement efficiently. So I remember the first neural network we trained when we finally got the automatic differentiation system working, and we had written a pure NX neural network. It was just trained on MNIST. And I remember that I think that was like maybe 6 or 7 months into the project when that first worked. And that was pretty awesome. And then we also, some of the first benchmarks we had were, we showed that the GPU compiled program with NX and EXLA were like 4,000 times faster than anything you can do natively in Elixir, and sharing some of those benchmarks. And people were like, this is crazy. I can't believe this is happening. That was a lot of fun too.
Yeah, with the COI messaging, this thing that we're working on is X% faster. That was kind of a lot of fun to watch too.
Yep.
And what about some moments that were particularly frustrating for you? What would have been some of the hard ones to break through? You mentioned the earlier one with kind of establishing that initial compilation, but what were some of the other ones that were pretty difficult?
Yeah, so the GPU one in particular, I just remember being incredibly frustrating. So I guess like high level, essentially what was going on there is that to compile a program to the GPU, specifically NVIDIA GPUs, TensorFlow and XLA were using something called PTX, which is like a NVIDIA assembler essentially. And they were calling it out from a subprocess using, I think like weight PID or something particular. And there's like something where on Linux systems, the Erlang virtual machine sets sigchild to I think sigignore or something specific, which essentially just results in the calling process of weight PID to completely like ignore the result of the program and return -1 or something insane. And like tracking that down took forever. Like that, and that's something that's pretty obscure about the Erlang, virtual machine that like only a few people would know off the bat, right? There was another very frustrating segmentation fault we were getting with convolutions on NVIDIA GPUs. And I remember just how frustrating it was kind of working with NVIDIA and trying to figure out what the deal was. And it turned out actually the reason for the segmentation fault was the default stack size for the dirty NIFs that we were using, which is kind of it's an Elixir specific thing. The dirty NIFs we're using, the default stack size was too small. And I had talked to some of the core team for Erlang a few times about this, and they kept saying, well, if you just set the stack size a little bigger, does it work? And I was like, yeah, I've tried that. It doesn't work, but I was setting the flag wrong or something. So it took me like 4 or 5 months to realize that I was setting the flag wrong. And I think NVIDIA had been telling me the same thing too. They were like, well, what's the stack size? Like, is the stack size too small? So that was frustrating, but that was probably more frustrating for me to realize, that I was making a silly mistake. It was like a typo or something and how frustrating it can be when you realize that, and you have a typo in your code that's been contributing to a bug for like 4 or 5 months now. That was frustrating. And there's been some, I guess, difficult moments in implementing like Axon. So, I think we have the benefit of being able to test against correct implementations in PyTorch and TensorFlow. But when you're implementing like numerical algorithms, getting exact like numerical correctness is very, very difficult. Like there's can be very subtle bugs that just pop up, and they have a drastic impact on the stability of like training different models and the predictions you get with different models. And so that can be very frustrating as well. I remember we implemented, so one of the things you can do with Bumblebee is stable diffusion. You can do image generation. And I just remember working for like 2 weeks straight trying to get the outputs we were getting from stable diffusion to match like within a very small precision of what you get in Python. And I also remember like thinking how insane, or how much admiration I have for people that are implement these algorithms from scratch without any reference implementation and without any reference tests or anything to say like, this is the correct implementation of whatever this algorithm is. So those are always very frustrating to try to track down those small bugs in numerical correctness.
So I have two more questions. They're basically wrap-up questions. One of them is make your last pitch for machine learning with Elixir.
Yeah. So I think those that are deploying, well, first, I honestly think that Elixir for machine learning startups is probably the best language that you can have, because you can do everything in Elixir, and not just everything from like a machine learning perspective, but also like from a like application development perspective. So with LiveView, you can write your front end in Elixir. With Phoenix, you can write really scalable backends with Elixir. You can have your entire inference pipeline written in Elixir, and it's fault tolerant and scalable. You can train your models in Elixir. You can deploy your models in Elixir. And I think for a startup that's undermanned or doesn't necessarily have large teams, you can build at a very high velocity. And I think that's something that you just don't necessarily get from another ecosystem. So if I was a small team, that is obvious. I think that would be the first language I would reach for, would be building an application in Elixir, because you can punch above your weight.
I like that. So you take JavaScript off the table, you take Python off the table, and you centralize everything on one language. That's wonderful. And I have one last question. Is there anything else that you want your listeners to know? What's coming up? What's happening?
Yeah. So I guess we've kind of ranted a little bit about machine learning and Elixir, but I definitely want the listeners to know, if you're not familiar with the machine learning and Elixir ecosystem, we have, I think, the perfect treat for you. So I just recently released a book, Machine Learning in Elixir. It's out in beta now, where you can learn the fundamentals of the machine learning ecosystem in Elixir from the ground up. So if you're not familiar with Elixir, it's a great way to learn the language. And then if you are familiar with Elixir and you're not familiar with machine learning, then it's a great way to learn machine learning. Machine learning in Elixir is, I would say, is designed to be the authoritative source on everything you can do with machine learning in Elixir. And it's got a lot of inspiration from some of my favorite machine learning books, such as, Francois Chollet's Deep Learning in Python was kind of the first book I ever read in machine learning. And then some of the other really popular machine learning textbooks out there, like Deep Learning by Ian Goodfellow and Yoshio Bengio and the other co-authors they have there. So I would highly recommend any listeners of these to go check out that book. Send me any errata you find, because it is in beta. So obviously there's going to be some issues as we upgrade the libraries and things change. But yeah, I think that's really one of my key focuses now, is just building out some of the educational material for people in the ecosystem to kind of, cut their teeth on.
Wonderful. That's a beautiful cap, going from genetic algorithms all the way to machine learning and Elixir. And so for Bruce and Sean, we've been talking for the GOTO Book Club, and we're signing off. Thank you.
Thank you, everyone.
Subscribe to the GOTO YouTube channel now and join the experts in person or online at any upcoming GOTO conference using the promo code Book Club. Visit gotopia.tech to learn more.